Pre-calc students, welcome to today's lesson 1.6. I hope you'll find this teaching technique to be useful for you as we may use it from time to time as the year goes on. I want to start with this. This section is about parent functions. You can see on the page in front of you that there are a library of parent functions. These are all listed in your book as well. All of these are pretty familiar to us with the exception of the last one, the step function. And it is important to note that we have two different notations to look at when we see a step function. You can see them both right there. The book tends to use the first of those two, but when you move to other resources, you may see that second notation, which we sometimes call it a floor function. And we'll talk more about that as we move on. Alright, so write the linear function that has the indicated values and then sketch. This will be a pretty quick problem. Remember, when we see f of 4 equals -2, that means that our input, or our x value, is 4. Our output would be our y value. That's -2. And in the same way, for f of 1 equals 5, we know that gives us point 1 and 5. So what we can do is just simply go and graph our 2 points, 1, 2, 3, 4, and -2. 1 and 5, and we can connect. And we've taken care of the sketch. One thing we haven't done yet is to actually write the linear function. Now you could try to look at the graph and pick it out, and I don't necessarily usually trust my graphs just in case I've had any error in the way that I wrote, or excuse me, the way I drew the line. So instead what I'm going to do is actually go through and find that slope. 5 minus -2 divided by 1 minus 4. We'll have -7/3, and then I'm just going to put it into point slope form, and you can choose either point. I've gone with the first one for -2. So y plus 2 equals our slope of -7/3 times x minus 4. We've already sketched the graph. The only thing I should note here is that it does say write the linear function. Down here I have an equation. If I want to change this to a function, I actually need to subtract the 2, and then I would just have y equals, and I could actually write that as a function rather than simply a linear equation. That's not something I'm super picky about, but to follow the instructions, that is what I should do. Onward. Alright, here we go. The greatest integer function, f of x equals the greatest integer of x, is defined such that x is the greatest integer less than or equal to x. So we're looking at that parent function you saw graphed on the first slide. Essentially what it means is you just go down to the closest integer value. Now when we see f of 11, we already have an integer there. That's just simply 11. Whereas f of 7.9, that's more than 7, and that's the next integer that's just below that. Alright, why don't you do those next two on your own. You can pause me and then hit play again. Okay, I'm back. F of 3/5, the integer that's directly beneath that would of course be 0. And then the function evaluated at -1.7, that would be -2. Remember, it's the integer that's below. And again, sometimes we see this written as a floor function. You may see the notation look like this at times. They mean the exact same thing. Alright, let's sketch this, and you have to think about what this graph would look like. Well, if I start at 0, I know that my function at that integer value includes 0, and everything up to 1, not including 1, would also drop right back down to 0. Once I hit the value of 1, I would move up because I now have an integer value of 1, and up until I hit 2, I would stay at 1. And once I hit 2, the function moves upward, and this pattern continues. The key to these functions is to find 2 consecutive steps. Once you have 2 consecutive steps, whether it's 0 to 1 and then 1 to 2, or as we do transformations, you'll see very different looking step functions. But once you have 2 steps, the rest of them just follow the pattern. So that's really all you need to be able to sketch the graph. All right. Evaluate the function at the given values, then graph. So here we go, f of 2 times the greatest integer of x minus 1. That's going to be 2 times the greatest integer of 3 minus 1, which would just simply be 2 times 2, which is 4. Our next one, f of 1.7, that's f of 1.7 minus 1. Now 1.7 minus 1, that's 0.7, so the greatest integer there is 0. 2 times 0 would equal 0. And then negative 1.7 would be 2 times negative 1.7 minus 1. Negative 1.7 minus 1 is negative 2.7. Our greatest integer then would be negative 3, and 2 times that would be negative 6. Now, if I'm going to graph this function, though, I'm actually going to, I could use those 3 values, but I actually want to go ahead and create a little chart. That's going to help this situation quite a lot. And what I would do is choose values like 0 and 1/2. And I could choose 1 and 1.5. And if you wanted to continue that pattern, you could with numbers like 2 and 2.5. Now, I haven't checked any of those values over here. Why don't you pause real quick, find those values, fill out your chart, and go from there. Okay, I've now filled out that chart. Let's go ahead and plot these points. 0, we're at negative 2, and again, that is inclusive. That circle needs to be filled in. I'm not going to actually mark 1/2 negative 2. I'm going to go ahead and jump to 1 and just create an open circle there. Then at 1, this jumps up to the value of 0, and it stays at 0 until we hit 2. Once we hit 2, our value goes up to 2. And again, every time you make that jump to an integer value at 2, or in this case, I'm ready for 3, remember that you fill in the circle because it's included on the next step. And I can go ahead and finish filling this out real quickly, and I've graphed all that's going to show here. Looking at our next problem, as you can see, it says to use the graphing calculator. So we're going to do that by punching this in. If you go to your y equals screen, 2.94. Now, this greatest integer function can actually be done directly on our calculator by hitting math, over to number, and down to number 5, which just says int with parentheses. And we can just simply punch in our greatest integer portion inside of those parentheses, and that will take care of the function for us. And we're going to add 3.7. Now, when I'm on the standard zoom 6, I get a window that looks like this. It's kind of hard to see what I'm looking at. But if you look back at the function, you can see essentially what we have here is some kind of strange quadratic. So let's adjust that window and increase that y-max. Let's try 50 and see if we can see this graph any better. Now can. As a matter of fact, if you increased that further and further, this graph would start to look more and more like an actual quadratic. Let's move on to the next example. Piecewise functions. Now, we've actually seen these in this course already, and you've also seen them in previous courses, AAT, college algebra, whichever you happen to take. Again, piecewise functions are functions that follow different rules at different places. So you can see on this particular function, f of x, it's linear up to and including -2, and then the graph changes to a quadratic shape after -2. Let's go ahead and create a little chart and see what this will end up looking like. Now remember, a linear function, when it comes down to it, we only really need 2 points. So I'm going to choose -5 and -2. It really is important that I get -2 in there because that's where the graph ends. So at -5, we'd have a value of 5 minus 2, so that would be 3. And at -2, we'd be 2 minus 2, which is 0. So I can go ahead and plot that graph, -2, 0, and -5, 3. And our line would only go, remember, to the left as the rule changes once we get to that -2 x value. Alright, so again, the rule changes. Let's take a look at the next rule. Now I know this says x is greater than -2, but we actually want to include it so we can see where this graph would in fact begin. So -2 squared plus 1 is going to give us 5. Let's go with -1 and 0 and see if we have a good idea what this parabola is going to look like. There's 1 plus 1, so that's going to be 2. 0 is going to give me 1. I believe, looking at this, we're going to need to go a little bit further because you can see that we're still moving downward. And I know this is a parabola that opens upward. So I'm going to go further and we'll do 1, and we know that would be at 2. And then at 2, we would be at 5. And I think this is starting to take shape. So let's plot these points, -2 and 5. -1, 2. And you can see the parabolic shape taking hold there. On our last example, go ahead and graph the first and third rules on your own. Pause the video, do that, and then pick it back up and we'll graph the second rule, the greatest integer function, together. Okay, I've now graphed the first and third rules and we're left with just simply the greatest integer function. Again, we need to choose some values that fit the ends of this rule, like for instance -3. And yes, I understand that -3 is not included. It's still important that we consider that point though. So -3, the greatest integer, is -3, add 2, and you get -1. I'm going to do -2.5. I'll get that same value. From here, I'm going to go -2 and -2, greatest integer is -2, add 2, and it's 0. At -1.5, I'd have the same value. At this point, I can actually go ahead and pick up the rule that we're going to be dealing with. Now, this has to be open here and open here. Once I'm at -2, that circle is in fact closed. And I'm going to continue. As I'm finishing these steps, there's one thing to notice. The step function actually ends with a value of 3, and when we're at 3, this step function tells us the value is 5. So we can go up here to this 3 and 5. Prior, that circle was open. Now it's closed. I hope you've enjoyed this lesson. Let's do some homework.